Hello student, myself Nimesh Prabhakar. Welcome to Process, Dynamic and Control lecture series. In my previous lecture, I discussed about leg in distillation cold. And first one leg we discussed, that means leg in liquid flow. Now, in this lecture, we discussed about another two type of legs. So which are that? First one we discussed about the leg in vapor flow. So in the vapor flow there is a leg associated, and first one we discussed about the leg in vapor flow, and then after we discussed about the concentration leg. So in this lecture we discussed about these two type of leg. So first one is a leg in the vapor flow, and then we discussed about the concentration. So now we start with the leg in the vapor flow. So the vapor space between the plate and the resistance at the plate from a series of interacting legs as far as vapor flow are concerned. The response is similar to that of a series of pressure tank where the flow out of the any tank depends on the pressure downstream as well as the pressure in the tank. So here we can compare this leg with the leg associated with the liquid flow rate. That means the series connection of the liquid tank. We already discussed the interacting and non-interacting type of the series connection of the liquid tank. So here we compare this example with this the leg in the vapor flow. So for the one tank we know, for the one tank with the equal resistance upstream and the downstream, the time constant is RC by 2. In the first one chapter we discussed about the interacting and non-interacting connection, and then we discussed about the leg or the time constant associated with this. So one tank with the equal resistance, the upstream and the downstream, the time constant is RC by 2. Same with the two tank and three resistance in parallel, that means at the outlet and inlet side. In the series, the transfer function relating pressure in the second tank and the input pressure for the first tank has effective time constant of RC and RC by 3. Adding more tank increase the spread between the largest and smallest time constant. So here from this example we can understand, so as we add more tank, that increase the spread between the largest and the smallest time constant. The leg in vapor flow is usually an order of magnitude smaller than the leg in liquid flow because of the small capacity of vapor hold on the plate. If this capacity were just the volume of vapor space, the vapor leg would indeed be the negligible, but the increase in pressure that goes with increase in the vapor flow. So here, if the capacity were just volume of vapor space, the vapor leg would indeed be negligible, but the increasing in the pressure that goes with increasing in the vapor flow means that the vapor must be condensed to heat the liquid to higher temperature. The holdup of liquid therefore acts as a capacity for vapor, which is generally much higher than the volumetric capacity in the vapor space. See here, this is the diagram. The material balance for the vapor flow for a single plate is given by this equation, as we know that the material balance equation is accumulation is equals to inflow minus outflow, or in other words we can say inflow minus outflow is equals to accumulation. So here we can write the term of accumulation as HB into dP2 by dt plus HL d theta by dP into CL by lambda dP2 by dt. And here from the figure we can say the inflow we can write as the P1 minus P2 upon R, that means pressure difference between that, and minus outflow we can write as P2 minus P3 upon R. Here this HB indicates the holdup in the vapor space and HL indicates the liquid holdup. Same as d theta upon dP indicates the change in boiling point with the pressure, and the CL indicates the heat capacity of liquid. Lambda indicates the heat of the condensation, and last one, the R indicates the flow resistance. So this is the equation for the material balance for the leg in the vapor flow. Now we discussed about the concentration leg. So now we start second one type of leg. So the name of this leg is concentration leg. The concentration leg describes the relatively slow change in the plate composition. That flow changes in feed composition or that occur after the change in liquid or vapor flow have reached all the plate. The liquid on the isolated, well mixed plate would show a first order response to change in the composition of the flow of either the entering liquid or the entering vapor state. So the value of effective time constant in this system depends on first one, slope of equilibrium line, then it depends on the plate holdup, then flow rate in column and feed rate. So the value of effective time constant is depend on these four parameters. That means the slope of equilibrium line, plate of holdup, then flow rate in column and feed rate. Now we discuss about the effect of equilibrium in line slope. So see, this is the diagram for that. So here consider a one stage separation and assume that the vapor composition is a linear function of a liquid composition over the range of composition covered. So we can write mathematically as y is equals to a plus bx. The dynamic response for change in feed composition is derived in the usual way. The symbols for the concentration of more volatile component denoting the change from the normal. So here, the dynamic response for the change in feed, the composition is derived in the usual way. That means the symbols for the concentration of the more volatile component denoting the change from the normal value. Here we can write the equation for this concentration leg as H into dx1 by dt is equals to F xf minus bx1 minus dxd. So here from equation number 1 we can write xd is equals to bx1. So we can get the equation as h dx1 by dt plus b plus small b into d into x1 is equals to fxm, and we give this equation as equation number 4. Now the transforming and rearranging this equation, so we can write the x1 by xf is equals to k upon ts plus 1. So the ratio of x1 and xf we can write as k upon ts plus 1, and here this k indicates the ratio of f upon b plus small b into d. That means it indicates the steady state gain, and the t is indicate the time constant, and we can write as t is equals to h upon b plus small b into d. So here k indicates the steady state gain, and we can denote as the k is equals to f upon b plus bd, and the time constant we can write as t is equals to h upon b plus bd. The time constant depends not on the relative volumetric volatility or on the difference between y and x, but on the rate of change of y with x. Now we discuss about the second effect of the feed rate and the total holdup. So for that, here we consider this diagram. The importance of this variable in determining the majority concentration leg can be demonstrated with the two-stage column. The equation for the column of figure are conveniently handled in the transformer notation. The change in vapor composition is taken as small v times the change in liquid composition. So for the top one plate, we can write equation as h1 dx1 by dt is equals to capital V y2 minus rx1 minus dxd. Then we can also write for the top plate as h1 into s plus r into bd into x1 is equals to b v into x. Same as we can write for the bottom one plate as h2 dx2 upon dt is equals to f xf minus bx2 plus rx1 minus by2. Or we can write for the bottom one plate as h2s plus b into small b into v into x2 is equals to fxf plus rx. So combining and solving for the x2 or x1, giving a quadratic expression whose factor represent the effective time constant as, so we can write the ratio of x1 upon xf is equals to bbf h1 h2 s square plus h1 capital B plus small b into b plus h2 r plus bd into s plus br r bd plus b square bd, or we can write this ratio as x1 upon xf is equals to k1 tas plus 1 or tbs plus 1. So x2 upon xf we can write as x1 upon xf, h1s plus r bd upon bb, and or we can write as x2 upon xf as k2 tcs plus 1 upon tas plus 1 upon tbs plus 1. So this is the value of x1 upon xf and x2 upon xf. So here we discuss about the concentration lag. So in this lecture we discuss about the two type of lag. First one is the lag in the vapor flow, and then after we discuss about the concentration lag. So total we discuss three type of lag. First one we discussed in my previous lecture. The type of lag is the liquid lag. Then we discussed about the lag in the vapor flow, and third one lag is the concentration. Thank you.